Hey, excuse me. Hey, friends. It's Ben again. This is a video for the Calc 3 class. We're looking at the notion of double integrals. The actual title of the section is something like integrals over more general regions or something to that effect. Okay, 15.2. So as I think I mentioned with the video for 15.1, I don't really treat these two sections as separate. And that is what I've generally found to be the most successful approach. Because if you treat the two sections as separate, you get this idea that everything is secretly a rectangle. And that gets you really messed up about how to approach these. So when we talk about double integrals, you will see that they write something with two integral signs stuck together, and then a subscript with a capital letter, and then a function, and then it'll say dA on the end of it. Okay, so that's what you'll see for a double integral. An iterated integral had integral constant to constant, integral function to function, or maybe constant to constant. Constants or functions, they're just not very interesting ones. And then function dx dy or dy dx, whichever. Okay. An iterated integral is how you evaluate a double integral. A double integral is an expression that's just kind of a shorthand for what you're going to end up doing. So the subscript capital letter is making a reference to what the region is that you're going to integrate over. So that's the main big things to think about as the difference between double integrals and iterated integrals. So let me put some pictures on here and we'll see how this goes. And that would be that. Okay, pause. Okay, friends, you should hopefully be seeing the double integrals front page on the screen there. So graphically speaking, what we need to think about are these regions that we've got here. In the case for this picture, the region is a rectangle, but we need to understand that the region could have any shape, right? Whatever shape that it has, once you've got that region, then it can be broken up into little bitty rectangles. And you think about each one of the little bitty rectangles as being a small piece of area. And we'll refer to it with this dA to represent a small piece of area, just like dx stood for a small piece of length when we were in Calc 1. So the picture that hopefully you can make out here is that we have a rectangular box. Its height is given to us by f of xy equals z. So you actually have some sort of a surface that is traced out here, and its height above the plane is going to be giving you the heights of these little bitty boxes. If you take and multiply a height times an area of a base, then you get a volume of a box. So this symbol we've got here, the double integral of the f of xy dA, is actually referring to taking a summation of the f of xi yj, so that just means f at some point in one of those many little rectangles, times the area of the rectangle, and then these sigmas are just referring to add them all up for all the possible I values and all possible j values, okay? Now, the difference between doing a Riemann sum and doing an integral is that a Riemann sum has a finite number of entries, and then you take the limit as the number of entries goes to infinity, and that gets you your integral, okay? So an integral is an infinite sum, And in a sense, then your finite sums are kind of like a finite version of an integral. So we generally think of these in terms of figuring out a volume that is under a surface, but that value that you got for your f could be anything that you could think about being evaluated for points of x and y. So if you were doing some sort of a statistics, probability sort of application in order to do some data analysis stuff, then you could certainly be thinking about two different variables being maybe someone's age and maybe their weight. That's one of my variables that I'm always worried about. Two of my variables I'm worried about, actually. But you would have something where you are looking at maybe the data counts for a particular age and weight range. Okay, just as an example there. Maybe more sciencey sounding, data science. I don't mean it's not a science. I'm just saying it's less of a natural science and more of a social science sounding thing. But more natural science sounding thing, you might talk about your region there, whatever the shape might be, being some sort of a plate, and the plate actually has different temperatures at different spots. And then the summation that you're talking about, you would have temperature or something expressing how much energy is being generated there because of the temperature, times the areas, and then you're adding them up somehow to figure out a total energy. Same sort of thing that it could be point charges. I want to say something about density, but I tend to think about density as more three-dimensional. So I'm going to save that more for the stuff we will do with triple integrals, which are coming up eventually. Okay. All right, so if you've got a surface that you need to find the volume beneath, then the way that you'll find it is to simply take the heights multiplied by, and then I goofed up. Hang on, folks, I gotta fix that as I go. And that was what, green? So DA. And it doesn't look like the same color green. Oh, well. All right, anyway, though, you're taking and essentially getting little bitty volume elements here by making those boxes from the previous page. And then the integral says add them all up. So if you need to find the volume under a surface, then you can just take and integrate the height of the surface, and it's going to end up being integrated with respect to both an x and a y. Now, this is totally not talking about doing the setup. We'll do the setup on examples here in a minute, though. So, oh, haha, like this one. So here we're asked to find the volume under the surface that's given to us by z being 6 minus 2x minus 3y. And it says in the first octant. Now, if you're saying, oh, what's an octant? I've never heard of that before. Well, you've talked about the first quadrant when you did things in algebra at some point. The first octant is the three-dimensional equivalent. The first quadrant is where the x and the y are both positive. So the first octant is going to be where the x and the y and the z are all greater than or equal to 0. Well, I should go ahead and say positive. All right. So if we look at a graph of z equals 6 minus 2x minus 3y, and if you can't do that just by quick sketching, go ahead and go to one of the drawing programs we've done. Once you've got a picture of it, use a snip tool. Don't do a whole screenshot or print out like a whole document or something. Do a little snip of the picture that you need, and then you can paste it into whatever program that you might have that you're going to deal with these PDFs with. Okay. All right. In any case, though, this z equals 6 minus 2x minus 3y. If you set the z equal to 0, then that means that you're going to have this line down here, which I guess I could probably jot down there. Let me try to get the right sort of color. I could jot down there that that's going to be 2x plus 3y equals 6 when you solve for it, okay? And then if you, then we are taking a look at the region that we want to do things across based on that, that quick little sketch that we have there. It's also helpful to figure out that we've got these points of intersection with the axes there because those are going to come into play. All right, so we're going to find that volume, and we can set that up with either order of integration. So I'm going to try to go along here and integrate and have 6 minus 2x minus 3y d something d something. And that's the way I always say it, d something, okay? And I'm going to do it dy dx first, right? So dy dx. And then we can come back later and do it dx dy if we want to, but in the interest of time, I think I'm probably just going to do it in one direction, right? So we have our sketch drawn there, and because it says dy on the inside, that means that I'm going to draw my arrow in the direction, oh, that was too small to see. Draw my arrow in the direction that y increases. dy means change in y. Y is increasing by going up. When I enter the region, I'm entering down here, and that's going to be at y equals 0. If you think you're going to have a hard time keeping track of these, write down y equals 0, okay? And then it is going to exit at this 2x plus 3y equals 6. Well, we're going to need to solve for y on that. Shouldn't be too hard to do. We'll just go ahead and say y equals 6 minus 2x and then divide by 3. If you're saying you can't do that in your head that fast, take more time to do it, okay? It doesn't have to be done as a race, okay? I am going to try to pretty that up a little bit and say 2 minus 2/3 x, all right? And then we can go back in there and just say my x values go from 0 over here to 3, all right? So 0 to 3. If you want to write x equals 0 and x equals 3, that's fine. But remember, outer limits are always going to be constants. Inner limits might depend on something, but if your inner limits are also constants, that means your region had better be a rectangle, okay? All right, so now that we've got that, we're going to go ahead and evaluate this. And so I'm going to write integral 0 to 3 here, and I'm going to put some square brackets. Since I'm integrating with respect to y, I get 6y minus 2xy minus 3/2 y squared. And then I'm going to have to evaluate that from y equals 0 to y equals 2 minus 2/3 x. Once I get it, I will have a dx. That is super duper messy and kind of jammed over there too far, so I'm going to try to move it so that it's not running into things quite so much. All right, so now it's the integral 0 to 3. And we are going to have to plug in that upper limit first. Wow, unfortunately my limits got kind of goofed up as I went along there. Sorry folks, that this is stuff you shouldn't have to watch because I should have been a little bit more cautious. So we're plugging in there 6 times the quantity, 2 minus 2/3 x, minus 2x times the quantity, 2 minus 2/3 x, minus 3/2 the quantity, 2 minus 2/3 x squared, and then minus, now we have to go back, and everywhere there's a y, we have to plug in a 0. But that means everything will end up as zeros. So we have an integral 0 to 3. I'm going to expand all this stuff out, and I'm probably going to need to go to a second page for it. So bear with me though. So 12 minus 2/3 of 6 is 4x, and then minus 4x here, and plus 4/3 x squared, minus 3/2 of, oof, now we got to square this. Let's see, 4 minus 2 times 2 times, so 8/3 x plus 4/9 x squared dx. Oof, gosh, that's messy. But it is all doable. I'm going to take and copy that and add another page here and paste. All right, so that's the thing that we are in the process of trying to evaluate. So we have an integral 0 to 3. All right, I can see I've got an x 4/3 x squared here, and then I've got to think about minus 3/2 times 4/9 x squared. That would be minus, well, I started to do that a bad way, but I can cancel a little bit here. So it would be minus 2/3 x squared. And I'm going to group that together with the other x squared that I've got. And when I subtract them, I should get 2/3 x squared. And then I need to get the ones that are just plain x's. So I'll get minus 3/2 times minus 8/3 x. And then, oh, look at those. So let's see, that would cancel a little bit, and we'd have 4 x's. But if, as you notice, we also had minus 4x and minus 4x there, so we end up with minus 8 plus 4, so minus 4x on that. And then finally, we need to mess with the constants. So minus 3/2 times 4 is minus 6. We're putting it together with a 12, so we end up with a plus 6 dx equals. All right, now we have to integrate those. And so you should end up with 2/9 x cubed minus 4/2. So 2x squared plus 6x, going from 0 to 3. And so plugging in the 3, 2/9 times 27 minus 2 times 9 plus 6 times 3, and all that minus, and you plug in the 0 everywhere, you get 0. So 2/9 of 27 is 6 minus 18 plus 18. Just cancel, we get positive 6. Bang, done. All right. Now, with regard to that sort of thing, just a tip, look back at your final answer and make sure if you're doing a volume, you got something positive. If you get a negative volume, you probably did something wrong. If you get a negative area, probably did something wrong. Okay. Another thing to mention with regard to that, there is no indefinite double integral. If you get a value at the end that has variables in it, and it was the variables you were integrating with respect to, then you just mess something up with the setup. Okay, so go back and look at what's happening. In general, though, You could have things where you're integrating and you have parameters in it, like maybe you're doing the area of a circle, and so your final answer will have a pi r squared in it. But you were integrating with respect to x and y, so you should get rid of those. All right, so let's look at another example here, and hope that nothing goes awry this time. Yay, all right, looks good. All right, so this time we're finding the volume of the upper hemisphere for x squared plus y squared plus z squared equals 1. So it is a sphere of radius 1 centered at the origin, okay? So since we're doing the upper half of the hemisphere, you can take this and solve for z, and we're going to take the positive part, and that's going to be the heights that we're given. So then we need to think about when you've got this and it's hitting the xy plane, that's z equals 0. So you can plug in 0 for z. We could have plugged it in over here, and you would be getting the x squared plus y squared equals 1 equation there on the plane, and then that's going to be your region of integration, right? So the base of this that it's sitting on the plane on is going to be the circle and its interior, right? So now when we do our integration on this, we are going to be integrating the height, the 1 minus x squared minus y squared. And I went ahead and made the choice to go dy and then dx. I tend to do that when it doesn't actually make a difference one way or the other. So let's go ahead and do that. And we have to think about the inside is dy. So that means that we are going to draw an arrow in the direction that y increases. And in so doing, we enter the region where the y is negative the square root. We exit the region where y is positive the square root, okay? And then we have to think about where are the x's going between. The farthest reaches are -1 to 1, okay? Now, then the next bit on working this out is to make an observation. Everybody makes this observation. It's not really making any progress. It's just that, hey, these 4 quadrants here, because of the function that you're dealing with, all of the volumes that you're going to get are be exactly the same. So instead of doing the integral like this, let's do 4 times the integral and go from 0 to 1 instead of -1 to 1. That would be 2. That would be a factor of 2. And then instead of going from the minus to plus, we'll go from 0 to that square root. Okay. So we are in that step there making use of symmetry. And I should have used something that was a little more readable there. Okay. So in order to do that integration, we either have to remember all those formulas from Calc 2, or have to remember how to do a trig sub, or we go consult the table and look up what the square root of a squared minus u squared is. So the a is going to be that 1 minus x squared. Because remember, as far as y is concerned, x is just a constant. So the a squared minus u squared, and you've got this expression here. So everywhere there's a u, you'll put a y. Everywhere there's an a, you would have a square root of 1 minus x squared. But of course, an a squared then will just be 1 minus x squared. So, all right. So I think I've got another page of these calculations. And I went ahead and just copied across what I was working on there. All right. So since my integral of this thing, I need to do this, then that means coming along here, the u over 2 would be y over 2. The a squared minus u squared would be the 1 minus x squared minus y squared. the a squared over 2 will be 1 minus x squared over 2. The u over a is going to be y over that square root. At which point you should tremble in fear, because now we've got square roots in denominators, and that just looks awful. However, to the rescue is how the limits are set up there, okay? And so when we come along here, we have to substitute square root of 1 minus x squared for the y's. And so this y becomes that, and this y becomes that, y squared becomes that, and this y becomes that. And that means the stuff inside of that inverse sign is going to be 1. Yay! And this stuff in here is going to be 0. Yay! So that's looking pretty nice, actually. Now minus, and now we have to plug in the 0 everywhere there's a y. And that means we've got a 0 over 2 here. That part's going to cancel out. We've got the 1 minus x squared times the inverse sine of 0. Inverse sine of 0 is 0, so that's going to be nice. So in fact, almost all the pieces here are going to be nice. The one thing that's left is the 1 minus x squared over 2 times the inverse sine of 1, which you should know is going to be pi over 2, okay? So then when you plug that in, you can go ahead and take the pi over 4 part and chuck it out to the front and multiply it by that 4. And now all we have to do is integrate 0 to 1 and 1 minus x squared. And you can totally do that. So we end up with pi times 2/3. At which point you say, wait, no, pi, that thing with spheres, that's 4/3 pi r squared. No, 4/3 pi r cubed. But this is the hemisphere. So if you need to do the formula for a sphere, you would double it. So since this is half a sphere, you would get 2/3. All right. So yay, we did that. It was horrifying because of this formula here, but you can totally look up formulas like that. If you're doing that in your homework, write into the homework, and I look this up in the table, and like tell me which formula it is in the table that you're using. Okay. I would advise you copy the formula down, and that way, if you copied it wrong or applied it wrong, you know, I can give you partial credit. Okay. Yuck. All right. So then the next sort of thing that we're going to do is this notion of getting a volume that is between two things. So we've got some upper surface and some lower surface. And if that's the case, then the heights that we're thinking about are just going to be the difference between those two. So top minus bottom, dA, and you integrate. Now, here is the tricky bit. That region may not be specified. You may have to look at the two surfaces and say, where do they intersect? And then that will essentially mean take F and G and set them equal to each other, and then see what you can do about writing that in order to figure out your region. Okay? That comes up often enough that it bears stopping and saying something about it. Once you've got the region figured out, then you just have to figure out how to set up, the iterated integral and evaluate it. Okay. So this one here, is going to ask us to find the volume above z equals x squared plus y squared, and below z equals 4. So I went ahead and drew the three-dimensional picture there for us. This is what's referred to as a hyperboloid. And no, it's not. I'm a liar. It's a paraboloid. And then we're going to have a flat top on it from just a plane. Okay. But then I go ahead and say that it's in the first octant. I spelled octant wrong, and I cannot let that stand. So the first octant, where 0 is less than or equal to y is less than or equal to x, and 0 is less than or equal to x squared plus y squared is less than or equal to 4. So this part you recognize is a circle. So I'm thinking about a circle with a radius 2 here. And because it says that we're less than or equal to it, then that means we have to be inside of the circle, right? And the 0 there would be the circle that has a radius of 0, you know. But you could make a more interesting one of these where it went between a radius 1 and a radius 2 or something. But then the other portion here says we want our y values to be less than our x values. So that means we draw the line y equals x. And now we've got kind of this tricky little piece to set up here, okay? So we have our choice of how to set this up. Nothing has specified it for us, but I am going to set it up, I'm going to set it up and have, let's see, the top is 4 minus, the bottom is the x squared and the y squared, okay? D something, d something. I'm going to set it up dx, dy. Now, you might worry as to how I knew to do that. So if I go ahead and draw my arrows in the direction that's up, like so, for having dy as the inside, then that means in some places the top is going to be y equals x, and in some places it's going to be that square root. And that means we would have to break it up into 2 integrals. And you can certainly do that. Some problems you just have to do that. But as much as possible, I like to avoid it. So I'm going to go in this direction, which has got the x's changing, and I'm going to hit those 2 curves. So the leftmost curve right here that I'm going to hit is, as we've said, y equal to x. So we're going to think about the y equals x, but because we are doing things dx, that means you're going to have the bottom be x equals y. All right, we're going to plug things in for x's. Then for the other bit on that, we're going to have to think about x squared plus y squared equals, what was it? 4. Okay, that's the outer edge. And we're going to have to solve for x here. So we get that our x is either plus or minus the square root of 4 minus y squared. And the way we make the choice about the plus or minus is it to the left or the right of the x-axis? Since it is to the right of the x-axis, then we're dealing with x equals positive square root 4 minus y squared. Okay, this could get pretty messy, but bear with. Then we have to say, where do our y values go between? The y equals 0 down here, that one's pretty easy, right? But then what you might be tricked into doing is saying, aha, I'm going to let my y go all the way up to 2 there. If you do that, you will end up with complex numbers because you've got a square root of some stuff. And no, you might not end up with complex numbers, I guess. But what we need to think about is that place right there. That place right there is the intersection of these 2 things. So we're going to have to put in y equals x to that. And that really says that you've got 2x squared equals 4, x squared equals 2, x is either plus or minus the root of 2. We can see from the position that we're talking about the plus square root of 2. Okay. All right, we've got this whole thing set up. Let's see if we can integrate it. Okay. So in the next step here, I'll write 0 to radical 2. And then the integral was dx, so I'll have 4x minus 1/3 x cubed, and then minus y squared x, and I'm going to evaluate it from x equals y to x equals the square root of 4 minus y squared. Close parentheses and do a dx. All right, that is probably going to be pretty messy. But so far, at least, we haven't had to look anything up in a table. All right, so we're going to substitute in the top limit first. So we'll have 4 times the square root 4 minus y squared, and then minus 1/3 of that square root, so 4 minus y squared to the 3/2 power. Man, it would be nice if that would distribute, wouldn't it? Minus, now we do y squared, so the square of the square root would be 4 minus y squared times x minus, goodness. And now I'm going to put some parentheses here, and I have got to clear some of the figuring off there. I will go ahead and put it back for later reference here in a minute. But now we need to plug in y for all the x's. So 4y minus 1/3 y cubed minus, let's see, y squared times y, so y cubed. I wrote dx to the outside, but it was supposed to be a dy. All right. So let me copy all this and make us another page. And on the other page, I'm going to print. All right, so this is the thing that we're working on. So we need to tidy it up so that we can actually finish it off. And this 4 radical 4 minus y squared, that's not really going to tidy up much. Minus 1/3 of, that's not going to tidy up either. But hang on, guys. I made a typo here. 4 minus y squared. So this piece down here, y'all, I'm sure y'all spotted that, and you were probably yelling at the screen as I made that mistake. I need to be thinking about this y squared and having a square root of 4 minus y squared plugged in there. Okay, yucky yuck. All right, so copy this stuff, copy, go to the next page, erase all this because it was supposed to be this instead. Integral 0 to root 2, 4, square root of 4 minus y squared. You know what? I'll bet, maybe not, but I'll almost bet that there's something nice that's going to happen here. Okay, minus y squared, square root 4 minus y squared. Getting pretty awful looking, isn't it? Minus 4y, and then these go together, and we'll have plus, because of the 2 minuses, 4/3 y cubed dy. Okay, so 0 to root 2, and I am going to take and factor off this square root everywhere that I can there and hope that something nice happens. So I'd have 4 minus 4/3 plus 1/3 y squared, and then minus another y squared there, square root 4 minus y squared. and then minus 4y plus 4/3 y cubed, all that dy. If 4 minus 4/3, that's going to be 8/3, and then minus 2/3 y squared, square root 4 minus y squared, minus 4y plus 4/3 y cubed dy. So, as you can see, the difficulty is really caused by that guy right there, isn't it? But also, this here can have a 2/3 factored out of it and be 4 minus y squared, right? That's this piece, and let me circle it in red maybe. So this piece here, and if we are able to do that, we've got an integral 0 to root 2, still messy, 2/3 quantity 4 minus y squared to the 3/2 power, okay? Minus 4y plus 4/3 y cubed dy. All right, so unfortunately, it looks like I'm going to a second page with it, but it is looking a little bit less terrible. Right? So if you like me are looking at that piece there and saying, I don't quite know how to integrate that, let's see whether I have a copy of the textbook here, a copy of several textbooks here, and let's see whether we have something with a square root, something to a 3/2 power. So forms involving a squared minus u squared. So it's looking like this kind of thing here, but I'm not seeing anything that is, wait, I don't have a pointer on this thing here, but look at formula 74. So formula 74 says to us that the integral of a squared minus u squared to the 3/2 power du is equal to minus u over 8 2u squared minus 5a squared square root a squared minus u squared plus 3a to the 4th over 8 inverse sine of u over a and then plus c. We don't have to worry about the plus c, but that formula there, do me a favor, you remember that, and then we'll go back and use it on the other map. All right, so, oops, this is equal to, and we're going to have a 2/3 of that thing that I asked you to remember, okay? So go ahead and remind me. That was minus u over 8, okay. Well, the y must be the u, so minus y over 8. What was it? 2u squared, so 2y squared minus 5a squared. Let's see, a must be 2, so a squared is going to be 4. Quantity square root 4 minus y squared for the u squared, right? Plus 3a to the 4th. Okay, so 2 to the 4th is 16. over 8 inverse sine of what? U over A. Okay, so y over 2 closed quantity. Ugh. And minus, now we have to do the integral of the 2y, I'm sorry, the 4y, so that's 2y squared, plus the integral of the 4/3 y cubed will be 1/3 y to the 4th. Evaluate from 0 to the square root of 2. Okay, thank you for remembering that for me. Okay, so now we have 2/3 of minus the y gets a square root of 2 over 8, 2 times y squared, so that'll be 2 times 2 minus 20, square root of 4 minus y squared, so 4 minus 2, so that'll be another square root of 2. Oh, that'll be nice. Plus, and we had a 3 times a 16 here, so that's going to be 6 inverse sine of square root of 2 over 2. Oh, wow, that was nice too. Okay, great. Minus 2 times the y squared, so square root of 2 squared is 2, plus 1/3 y to the 4th. Let's see, square root of 2 to the 4th would be 2 to the 2nd, so that would be 4. All right. And then minus 2/3 of, now we have to plug in a 0 everywhere there's a y. And that means all this will disappear because it's got a 0 as a factor, and all this will disappear because it's got a 0 as a factor. And so does this, and so does this. So we get to just write a 0 there. Thank goodness. So 2/3 of minus, and these square root 2's will go together, and then you'll have a 2 over 8 times, let's see, this one here is 4 minus 20, so negative 16, plus 6 times, oh my, inverse sine of root 2 over 2. Oh, you said that's pi over 4? Okay, thanks. And then minus 4 and plus 4/3. All right, this and that, we get 4. Those cancel. 2/3 of 4 plus 3 pi over 2. And oh look, a minus 4 and a plus 4/3. Oh, that was lucky. Those 4's cancel out there. And now when we take that 2/3 through there, 2/3 times 3/2 will be 1, so we get just a regular pi. And 2/3 times 4/3 plus 8/9. Whew, and then we're done, okay? I do not guarantee my arithmetic, but that is a fairly hard example worked out to completion. These are all doable, maybe not super easy sometimes. If you have trouble with the integration, use your tools. You have online resources like Wolfram Alpha that will do the integration for you. If it gives you a super weird answer, maybe question whether you got it set up just right, okay? But in any case, that gets you a few examples, and I'm pretty sure that you can do these, okay? All right, see you in class.